All right, ladies and gentlemen, actually we didn't have time last time, I think, to make it through the entire example, so we'll spend this period going through our non-ideal refrigeration cycle example. And then when we're all done with that, we will talk about methods for improving performance for a refrigeration cycle, the big one, which is kind of like a regenerative cycle, if you like. Regeneration in this refrigeration cycle was called flash cooling. So we're going to finish off the lecture by discussing one way to implement regeneration, if you like, in a refrigeration cycle, and therefore increase the heat transfer and possibly reduce the work, increase the COP, for example, and that's called flash cooling. It involves using multiple compressors and multiple throttles. So it's actually a multi-stage compression process in the refrigeration cycle, and it results in a higher COP. So using this flash cooling technique, using flash cooling. So hold on a second. Sorry about that. Okay, so let's do our example. Let's do our example here. So we have a non-ideal vapor compression refrigeration cycle here. So we have the inlet temperature and pressure for the compressor. So here's the compressor inlet state, state 1. I have minus 10 degrees C and a pressure of 0.14 megapascals. By the way, in terms of bar, that's 1.4 bar. The working fluid, and the working fluid is a special chemical, a refrigerant, called R134A. These refrigeration cycles don't use water. They use a special fluorocarbon, so a mixture of fluorine, chlorine, and other chemicals. Sometimes they use propane. Sometimes propane is used as a working fluid. Nevertheless, H2O is not used in these cycles. We're using R134A as the working fluid in this cycle. So the R134A is compressed up to a temperature of 50 degrees C and 0.8 megapascals, so 8 bar. And then we have the fluid passing through the condenser, and it gets condensed. So let's see, state 1. Well, we'll put up the states in just a moment. So the working fluid R134A gets condensed in the condenser. So we pass through the condenser, and we have a pressure drop. We have a small 0.08 megapascal drop in pressure in the condenser. Okay? And then we end up at a temperature of 23 degrees C after the pressure drop through the condenser. And then the working fluid is throttle. I'm going to use the universal symbol for throttle here. I used a box here before, but just make 2 lines and connect them, and that's the universal symbol for a throttle. Remember, a throttle is a restriction. A restriction followed by a widening. So that's the indication there for the universal symbol for a throttle. The pressure drop as the fluid boils in the evaporator and extracts heat from a cold place is 0.1 bar or 0.01 megapascals. The mass flow rate, so m dot for the R134A. R134A is 0.05 kilograms per second in the cycle. What are we supposed to find? We're supposed to find the heat addition or heat absorbed in the evaporator, the rate of heat transfer in the evaporator, the compressor power, W dot compressor. We're supposed to also find the isentropic efficiency for the compressor. Notice we have inlet and outlet temperatures and pressures for the compressor, so we can, in theory, find out the isentropic efficiency. And then let's find out the coefficient of performance. If this is a refrigerator, that would be Q dot low or Q dot evaporator divided by W dot compressor. So let's calculate the coefficient of performance for this device. Okay, so let's first of all, let's get the isobars of interest in the TS diagram before we get started cranking through some of this. Let's figure out what pressures we're at and where. So the minimum pressure is going to be the compressor inlet state, and that's at 1.4 bar or 0.14 megapascals. So P1 is our minimum pressure in our cycle, and it's 0.14 megapascals. The maximum pressure in the cycle is the compressor outlet pressure, and so that is 0.8 bar. So there's our maximum pressure at 0.8 bar. Now, apparently we have a pressure drop in the condenser. So the difference between P1 and P2 is 0.08 megapascals. So I have a P3 here, which is P2 minus the pressure drop. So 0.8 minus 0.08 megapascals, and I get 0.72 megapascals. That's going to be P3, which is my condenser outlet pressure. So the pressure here, P2, is 0.8 megapascals. And then I got a pressure drop across the condenser, so P3 is 0.72 megapascals. P1, of course, is the minimum pressure in the cycle at the inlet, which is 0.14 megapascal. That's the minimum pressure in the cycle, which is my compressor inlet pressure. The fluid passes through the throttle, and then there's a pressure drop in the evaporator of 0.01 megapascals. That means that the inlet pressure at the evaporator must be the outlet pressure plus the pressure drop. So pressure at the inlet of the evaporator is 0.15 megapascals. So the pressure drop across the evaporator is 0.01, but I have to add 0.01 megapascals to the final outlet pressure in the evaporator, okay? Okay, so we have our pressures here. So P4, 0.15 megapascals. Okay, so I got my isobars here. So let's get on here. Let's get on with this and calculate the heat transfer here. Let's calculate the heat transfer, the work, et cetera, et cetera. Okay. Analysis. Okay, to get the heat transfer in the evaporator, I need to know something about the inlet and outlet specific enthalpies. I know the mass flow rate for the R134A, our working fluid, our refrigerant, but I don't know the inlet and outlet enthalpies of the evaporator. So I'll tell you what, let's try to solve for W dot for compressor first. We have temperatures and pressures here and here. Maybe it will be easier to get W dot for the compressor first. Let's get W dot for the compressor first, okay? Okay, so apply the energy balance. So let's look at process 1 to 2. That is adiabatic compression in the compressor. Adiabatic. Oh, I guess I better, this is not going too well. Let's see here. Is that any better? That looks a little better. Now it has something to focus on, I hope. So let me remind you here that for, I need to put it in, I don't really have any assumptions here. Let's see here, assumption. So we have adiabatic, compressor, and the throttle's adiabatic too. Guess I better do that. There might be one or two more assumptions, we'll see. Of course, steady state, steady flow, as always with these problems. Okay, is equal to H evaluated on the inlet condition, so that's evaluated at -10 degrees C and 1.4 bar. Okay. Let me show you where you get properties for R134A here. You may have to do some interpolation, depends. But let me show you where the properties are. So if you start with, so we have H2O tables before, saturation temperature table for R134A, refrigerant R134A. It's a fluorocarbon, so it uses fluorine and carbon, and it is a refrigerant. So temperature table, just like for H2O. Pressure table, just like for H2O. Temperature, specific volumes, internal energies, enthalpies, entropies. Superheated vapor tables for R134A. Okay, we're going to use these just like we do for water. Now we have negative 10 degrees C, 1.4 bar. Let's see if we can find it here. Here's 1.4 bar. Negative 10 degrees C, specific enthalpy, 243.4 kilojoules per kilogram. By the way, I'm going to put the specific entropy up as well. Let's see what the entropy is here. That way I can see if the process is isentropic. If it's not, it's irreversible, and I know how to draw the process on the TS diagram. Okay. So H1 is 243.4. 240, I'm sorry, is it 234.4 or 243.4? 243.4 kilojoules per kilogram. And this is from table, superheated vapor table for R134A, B7, out of the notes. Okay? By the way, specific entropy, S1 at negative 10 degrees C and 1.4 bar. I'm going to put that in as well. That is 0.9606. 0.9606 kilojoules per kilogram degree in Kelvin, also from the same table. Let's look up, so now I have H1, let's look up H2. So H2 is equal to H evaluated at 50 degrees and 8 bar. 50 degrees C and 8 bar. Let's see if we can find that. 50 degrees C and 8 bar. $50 degrees C, 8 bar. Let's find 8 bar, maybe. Hopefully it's a superheated vapor. Here we go. 50 degrees C, so we get 284.39. So I guess 284.4. And here's our specific entropy right here, okay? So 284.4 and 0.97. 284.4. 284.4 kilojoules per kilogram, again from B7. And specific entropy at state 2 is equal to 0.971. 0.971, and that's kilojoules per kilogram degree in Kelvin from the same table. So immediately, we can now calculate the work or power. Let's see here. So M dot for the working fluid, R134A. M dot for the working fluid is 0.05 kilograms per second. Is it do okay? Seems to be all right. So we get equals 0.05 kilograms per second. That's for the working fluid, the refrigerant. H2 is 284.4 kilojoules per kilogram. H1 is 243.4 kilojoules per kilogram. Kilograms cancel out and we get kilowatts. And I have a specific work, 2.05 kilowatts. I'm sorry, I have a power, 2.05 kilowatts. So W dot for the compressor, 2.05 kilowatts. Okay? Let's go put this over here. .05 kilowatts. Don't have a lot of room here, do I? Oh, W dot, compressor, 2.05 kilowatts. Okay, put a box around that. All right. Okay, so let's start drawing our TS diagram here. We can figure out what's going on. First of all, H1, state 1, we got this from a superheated vapor table, and so was state 2. That was from a superheated vapor table. Also, notice that S1, 0.96, is less than S2, 0.97. So delta S is positive through the compressor. If the compressor is adiabatic, we're assuming adiabatic compressor and throttle, that means that entropy is being generated within the compressor and it is an irreversible process. Okay? So state 1 is a supercooled liquid, superheated vapor, sorry. And then we have an irreversible compression process. So here's 2 and here's 2 sub S. Okay, there we go. How about we try calculating the isentropic efficiency for the compressor? Let's do that next. We're supposed to calculate the isentropic efficiency. While we're at it, let's calculate the isentropic efficiency, okay? So the isentropic efficiency for the compressor is going to be equal to W dot of the isentropic compressor divided by W dot for the actual, the real compressor, dividing through by M dot for R134A, the working fluid. So M dot R134A, this times the specific work for the isentropic compressor, M dot for the R134A, W for the compressor, these cancel out, and I get the ratio of the specific work. So I get W isen compressor over W of the compressor. Now, if I apply the energy balance to the isentropic compressor or the compressor, I get a delta H across the compressor. You can see it here. So W isen compressor is going to be H2 sub S minus H1, and then I have H2 over H1. Now, I already have H1 and I have H2. I don't have the specific enthalpy for the isentropic process, compression 1 to 2 sub S. I need to find H at P2 with the same specific entropy as state 1. Okay? So let's get that. So H2 sub S is equal to H evaluated at a pressure P2. Let's see here. P2 was 8 bar, and S equals S1, and S1 is 0.9606 kilojoules per kilogram degree in Kelvin. Okay? Well, clearly, I'm going to have to do some interpolation here. Let's have a look. Let's go to the superheated vapor tables. And, oops. So let's see here. We are at 8 bar. And I want a specific entropy of 0.9606. So here's specific entropy, 0.97, 0.93, almost 0.94. So clearly the specific enthalpy of state 2 sub S, that's the outlet for the isentropic compressor, is going to be somewhere between these two. Okay, so you have to do a little bit of interpolation. Okay, so I do the interpolation and I find that H of 2 sub s, let's see, I have it here somewhere. I'm pretty sure I have it. Yes, H for 2 sub s is 281.05. 281.05, and this is from interpolation of superheated table B7. Interpolation from superheated vapor table B7, okay? So I've got H2 sub s now. All right, well, let's plug in. Let's see here, 281.05 minus 243.4 divided by 284.4 minus 243.4. They all have units of kilojoules per kilogram, and the unit cancel out, and I get an isentropic efficiency of 92%. 92%. 92% isentropic efficiency. So, eta Isen 92%. Eta isentropic efficiency of the compressor. %. 92%. There we go. Okay. Okay, what's next? We've done the isentropic efficiency. We've done the compressor power. Oh, we're supposed to calculate the heat transfer to the evaporator. In other words, Q dot low. Cold place, hot place. Okay? All right, let's calculate Q dot low. Maybe we have some information. We shall see. We'll see if we have enough information. Oops. Okay, so let's find Q dot low. So Q dot evaporator. That's Q dot low, Q dot evaporator. Apply the energy balance to my evaporator. Inlet state is state 4, outlet state is state 1. So I have Q dot evap is equal to M dot H1 minus H4. Applying the energy balance. R134A, H1 minus H4. Now I have H1 and I have M dot for R134A. I don't have H4. I do not have the evaporator inlet temperature, inlet enthalpy. Okay, so I need to do that. I need to get that. So let's look at process. Let's look at the expansion in the evaporator and the throttle. Let's look at the expansion in the throttle. Let's look at this process 3 to 4. If I know the enthalpy at state 3, I can maybe get the enthalpy at state 4 if I focus on this process. And by the way, state 3, what do I know about state 3? I know the temperature, and I actually know the pressure here. It's 0.72 megapascals. So I should be able to get the specific enthalpy at state 3, and looking at the process, the expansion through the throttle, I should be able to relate it to state 4. Okay. So let's look at the expansion process in the throttle. So process 3 to 4, and this is the adiabatic expansion in the throttle. In the throttle, okay? And of course the throttle, so here's our throttle right here. This is state 3. Here's our throttle. It's a restrictor. And we end up at state 4. Let's see here, the pressures here. Let me put the temperature and pressure. T3 is equal to 26 degrees centigrade. And P3, we already calculated that. P3 is 0.72 megapascals or 7.2 bar. 26 degrees and 7.2 bar. So I can get the inlet enthalpy. So 7.2 bar. Now, if I apply the energy balance to this thing, it's assumed to be adiabatic, it's insulated, so there's no heat transfer. There's no wires, there's no shafts in there, it's just a restrictor, that's it. A restrictor, there's no wires, no shafts, no impeller, so there's no work. So if we neglect changes in kinetic and potential energy also across the throttle, the E-balance says 0 equals m dot of the working fluid, R134A, H out minus H in, or if you like, as I said before, H4 equals H3. It is a isenthalpic device. H4 is equal to H3, so it's isenthalpic. If I find H3, I will have H4, and I can calculate my heat transfer. Okay. Let's see here. H3 is equal to H evaluated at 26 degrees C and a pressure of 7.2 bar. 7.2 bar. Okay? Let's see if we can find these pressures and temperatures in our tables. So here's superheated. Let's go to the saturation table first. Remember, state 3 is probably going to be a liquid, some kind of a liquid. So let's go to the saturation tables. Here's 26 degrees C. All right. So the saturation pressure at 26 degrees is 6.8 bar. We are at 7.2 bar. So note, P sat at 26 degrees C is equal to 6.8 bar, and we're at 7.2, so we are at a higher pressure than the saturation pressure, so we're a supercooled liquid. 6.8 bar, which is less than P3, which is 7.2 bar. So the conclusion is super cooled liquid. State 3 is a supercooled liquid. State 3 is a supercooled liquid because we're at a higher pressure than the saturation pressure. So this is going to be approximately equal to, now there's a long formula here. Oh, where am I going to do this? Let's see here. H for a super cooled liquid is approximately equal to U of the saturated liquid evaluated at the temperature plus the specific volume of the saturated liquid evaluated at the temperature times the pressure difference minus P sat evaluated at the temperature. We went over this a long time ago. Probably haven't used it very much. Remember, U for a supercooled liquid is approximately equal to U sat liquid at the temperature. Specific volume for a supercooled liquid is approximately V sat liquid at the temperature. So I'm using the definition of enthalpy here. Using the definition of enthalpy here. Okay? Using the definition of enthalpy, and then I got to add in V sat liquid, P sat liquid, all at temperature T. Okay, running out of space. I'm going to group these terms together, and I get approximately H sat liquid at temperature T plus the difference. V sat liquid at temperature T, P minus P sat at T. So I'm using the approximation here to get H for a supercooled liquid. We went over this long time ago, when we talked about properties. That was what, back chapter 2, I think it was, okay? All right, so let's look up H sat liquid at temperature T. So H of the supercooled liquid, so H sat liquid at 26 degrees C. Let's look that up. Well, that's going to be equal to, let's have a look. H sat liquid. Here we are. 85.75. 85.75. 85.75 kilojoules per kilogram. And then I have the specific volume of the saturated liquid times the difference in pressure compared to the saturation pressure. So let's get the specific volume here at 26 degrees. For the saturated liquid, it's 0.83 times 10 to the minus 3. 0.83 times 10 to the minus 3. So V sat liquid at 26 degrees C, 0.8 times 10 to the minus 3 cubic meters per kilogram. And then, of course, I have P sat at 26 degrees C. What did I say it was? 6.8 bar? Let's have a look. 6.8 bar. Good. 6.8 bar. 6.8 bar. Okay, now I'm ready to use this approximation here. So H sat liquid at 26 degrees is 85.75 kilojoules per kilogram plus the specific volume, 0.8 10 to the minus 3 cubic meters per kilogram. And then I have the difference in pressure between my state, which is 7.2 bar, in kilopascals, that's 72 kPa, minus the saturation, which is 68 kPa. 72 minus 68 is 4 kilopascals, times 1, basically 1, times 10 to the minus 3. So I get 4 times about 1, so that's 4, times 10 to the minus 3. 4 times 10 to the minus 3, added on to 85.75. So this term here is approximately equal to 0. Pressure is not much different than the saturation pressure. So I can ignore this term, and I get approximately 85.75 kilojoules per kilogram. In other words, H3 is equal to H evaluated at 26 degrees C and 7.2 bar is approximately equal to H of the saturated liquid, H of the saturated liquid evaluated at 26 degrees C, which is 5.7 kilojoules per kilogram, okay? So now I have, so now I have H3, and notice H4 equals H3 because we have a throttle. So now I have H4, check, I have everything I need. I have everything I need. Okay, let's calculate the heat transfer. Let's calculate the heat transfer. Equals 0.05 kilograms per second. H1 is 243.4 minus 85.7 kilojoules per kilogram. Kilograms cancel out and I get kilowatts. And I get a heat transfer 7.88 kilowatts. So let me write this over on the other side, 7.88 kilowatts. So Q dot evaporator, 7.88 kilowatts. Okay. I have W dot for the compressor. Now I can calculate the coefficient of performance. That's easy to do. For this refrigeration device, this is a refrigerator. Let's calculate the coefficient of performance for this refrigerator. So COP, if this is a refrigerator as opposed to a heat pump, what we're interested in is Q dot low, which is Q dot evap, divided by W dot in, which is the compressor power. So I got Q dot evap minus W dot compressor. Let's see here, Q dot evaporator was 7.88 kilowatts. And W dot for the compressor was 2.05 kilowatts. And I get a coefficient of performance 3.85, 3.85. So for every unit of compressor power, you feed into the device, you run the device with, you get 3.8 times units of heat transfer. Okay, so let's write this down. 3.85, COP. COP, refrigerator, 3.85. You know, I haven't done my TS diagram. Let's finish doing the TS diagram. Let's see here, state 1 to 2, and then we have heat transfer out of the condenser. Remember, we have a pressure drop in the condenser. State 3, as you recall, was a supercooled liquid. So I end up on this lower pressure isobar, that's state 3 right there. So I go down here. Let me use a different color chalk. Up, down, Then I skip down to my lower pressure isobar, end up somewhere as a supercooled liquid at state 3. And then I have isenthalpic expansion in the throttle. And then I have a pressure drop in my condenser, evaporator, as I add heat. Q evap. Okay, so there's my TS diagram. Note the pressure changes, the pressure drops. So the lines are discontinuous here, okay? Lines are discontinuous. Let's do one last little thing here. Let me put this in a kitchen. This is a refrigerator. Let's put this thing inside of a kitchen. So let's say, have a little bit of room here. So we got your kitchen. So you got your kitchen up here, that's your warm place. And your kitchen has a temperature, I'm just gonna give some numbers here. Your kitchen has a temperature of 25 degrees C. T high equals 25 degrees C. 25 degrees C. And then down here we have your ice box, your freezer, refrigerator. Ice box. That's where the heat is being extracted. That's your low temperature right there. Let's see here, the low temperature, -8 degrees C. By the way, we need to be a little bit careful with these temperatures. The kitchen temperature, where we're rejecting the heat in the condenser, the kitchen temperature always has to be lowest than the highest temperature during the condensing process. So the kitchen temperature needs to be lower than T3. T3 is at 26 degrees centigrade, so the kitchen is just 1 degree below that. If the kitchen temperature were higher than the minimum temperature, let's say it were at 28 or 30 degrees C, then heat would not flow out of the condenser into the kitchen. So the kitchen temperature, or T high, must be lower than the lowest temperature in your condensation process, which is T3. Same thing with the evaporation process. The evaporator has to be colder. The evaporator has to be colder everywhere in the evaporation process than the icebox temperature, because we want heat to flow from the relatively warm icebox to the cold evaporator. Now, the minimum temperature in my evaporation process would be, I guess it would be down here. We would have a, I guess it would be a TSAT at pressure P1. Let me make sure I have a low enough pressure here, temperature there. Let's look at TSAT at P1. Let's see here. TSAT at P1, let's see here. P1 is, what was P1, the low pressure? That's 1.4 bar. 1.4 bar, the saturation temperature is -18 degrees C. -18 degrees C. Okay, so I might have to adjust this temperature a little bit. We'll see. I guess I'm all right. So this TSAT is -18 degrees C. So, and actually, the highest temperature in my evaporator is at state 1. So T1 is equal to -10 degrees C. So the lowest temperature was 18 in my evaporator, and the highest was negative 10 degrees C as the fluid goes through my evaporator. Now, the highest temperature in my evaporation process is negative 10, and that's lower than negative 8, so heat will flow from the icebox into the evaporator all the time, regardless of whether we start off at negative 18 and go to negative 10. So heat will always flow into the evaporator. So here, let me make sure we're all clear on this. For the refrigerator to work, note, T high must be less than the maximum temperature anywhere in the condenser. The condenser temperature, the fluid goes into the condenser at T2 and leaves at T3, and temperature at T2 was 26 degrees, as I recall. Okay? And T low must be greater than the maximum temperature during the evaporation process. The maximum temperature during the evaporation process is T1, so that's the evaporator exit temperature. So T1 was negative 10 degrees C, so I have to be greater than that. I'm at negative 8. Looks good. Let's calculate the Carnot efficiency for a device operating between the kitchen and the icebox. COP max, and this is for a refrigerator. That's going to be equal to Q dot low divided by W dot of the compressor, or W dot in. And that's going to be equal to 1 over Q dot high over Q dot low minus 1. And that's going to be equal to 1 over T high over T low minus 1. And in our case, T high is 25 degrees C, so 25 plus 273 to convert into Kelvin, and negative 8 plus 273 to convert it into Kelvin. And I get a maximum COP. I get a maximum COP of 7.16. 7.16. So the maximum COP is 7.16. I get 3.85. A Carnot refrigerator would get 7.16. This guy gets half that due to irreversibility, okay? Irreversibility in the compressor, irreversibility in the throttle, irreversibility in the temperature jumps or temperature difference between the evaporator and the icebox and the condenser and the kitchen. Okay, let's take a break for a second. Okay, let's finish up by talking about a strategy for improving the coefficient of performance for a refrigeration device. So ways to improve the coefficient of performance include either reducing W dot or increasing the heat transfer, either from the low temperature place or from the high temperature place, okay? So we can increase COP by decreasing the work, the compressor work, or by increasing the heat transfer in the evaporator, for example, the heat transfer in. Now, one way to improve the heat transfer significantly at the evaporator is to try to make sure that the evaporator inlet state is as close to a saturated liquid as possible. Remember the delta H, so we have an inlet and an outlet specific enthalpy at the evaporator. The larger the delta H, the more heat can be absorbed. So if we can make sure that the inlet enthalpy at the evaporator is as close to a saturated liquid as possible, we can increase the heat transfer in the evaporator. Now, one way to do this is to use what's called a flash chamber. use a flash chamber. So let's, there's the device right there. Let me just draw the TS diagram so we can see what's going on. So here's our saturation dome. I'm going to assume there are no pressure drops across the evaporator and the condenser, so there's no little delta P. However, there are going to be 3 pressures in this device. Notice that we have multiple stages of compression and multiple stages of expansion. We got 2 compressors, a low pressure and a high pressure compressor with an intermediate pressure in between. And then we have 2 throttles, a high pressure throttle and a low pressure throttle with an intermediate pressure, okay? So there's going to be some intermediate pressure here. So I'm going to say P3 is equal to P2 is some intermediate pressure Pi, and of course P1 is the minimum pressure in the cycle, and P4 is the maximum pressure in the cycle, okay? So I'm going to put in the 3 isobars. So here's our Pmin. Here's our Pmax. Here's our intermediate pressure, which is somewhere in between. So here's our intermediate pressure Pi, okay? So let's say that state 1 starts off as a, I don't know, a saturated, I guess I can make it superheated vapor. So state 1 is a superheated vapor going into the low pressure compressor. Low pressure compressor inlet, let's say it's a superheated vapor at state 1. Of course, these compressors may have some irreversibility associated with them, so maybe there's a path right there. So that's state 2. Now let's talk a little bit more here about how this device works. Let's now go to the outlet state for the condenser. So let's say that we are a super cooled liquid. Let's say it's state 5. So let's jump to the outlet of the condenser. So we're some kind of a liquid here going into the high pressure throttle. Now the high pressure throttle expands the liquid isenthalpically. So here's our isenthalpic expansion, and we end up at state 6. Now what I'm going to do here is I'm going to separate, so notice state 6 is inside the dome. It's mainly liquid, but there's a significant vapor component. Quite a bit of vapor in there. I'm going to separate out the vapor. So here we have saturated vapor. And I'm going to separate out the liquid. So here we have saturated liquid. I'm going to do it in what's called a flash chamber. It's just a big chamber with a drain for the saturated liquid at the bottom and a vent for the saturated vapor at the top. So I'm going to separate out the liquid, saturated liquid from state 6, and the saturated vapor, and only the saturated liquid is going to go into the second low pressure throttle. So state 7 is now a saturated liquid. So this is state 7 right there, saturated liquid, because we have separation in the flash chamber. It's just a separation chamber, okay? Separates out the liquid and the vapor. And of course, the liquid, saturated liquid, is now going to expand in the low pressure throttle, and we will end up at state 8. Now, I want to point out something here. If, don't write this down, if we didn't have this flash chamber, which separated out the saturated vapor and the liquid, and we instead just throttled all the way down to the minimum pressure, then our path would look something like this. And our final state inlet at the evaporator, so this would be our final state 8 at the evaporator inlet. Notice there's a lot more vapor in this state 8 than the state 8 with the flash cooling, okay? So the quality, much more vapor if we don't have this flash chamber and separate off the saturated vapor before we pass it through the remaining throttling. So the idea of having this flash chamber means that we get much more liquid and therefore much more ability to cool in the evaporator. The specific enthalpy at state 8 is much lower than it would be without the flash cooler. And therefore we can have a lot more heat addition. Q evap, which is equal to H1 minus H8. A lot more heat transfer in the evaporator if we pre-separate the vapor and the liquid, send the liquid through the final throttle and into the evaporator, and send the vapor that was separated out. Pipe the vapor into a mixing chamber, and then pressurize it in the high pressure compressor. So we're going to take low enthalpy saturated vapor, pipe it into a mixing chamber where it mixes. So the enthalpy that's being siphoned off from the flash cooler, there's our H. So if you want to know the, so this is, I'll call this state 9. There's state 9. So this is state 9 right there. This is saturated vapor at the intermediate pressure. So we're mixing enthalpy at state 9. So this is saturated vapor at state 9. We're mixing it with superheated vapor at state 2, and we're ending up at some intermediate state, state 3. Cool vapor, super saturated vapor, relatively cool, superheated vapor, mix them together, you get a warm, not cold, not cool, not hot, a warm, superheated vapor. And then we compress all the way up to state 4, okay? So the entire process kind of looks like this. 1 to 2, skip over to 3, 3 to 4, transfer heat in the condenser. So Q condenser, expand in the throttle, skip over to a saturated liquid, expand one more time, reject heat in the evaporator. That's what it looks like. That's what the process looks like. This has the effect. This has the effect of increasing Q dot low because we have a greater enthalpy change in the evaporator than we would have had if we expanded all the way down without flash cooling. So it increases Q dot low. It also increases the specific work just a little bit, and therefore W dot just a little bit. But typically, this results in a COP for the refrigerator going up. So this is a way of increasing heat transfer in the evaporator by making sure that there is more liquid in the saturated mix as it flows into the evaporator. More liquid in the saturated mix at the inlet of the evaporator. And therefore, we have a higher heat transfer capacity in the evaporator. Okay? So this is called multi-stage compression with flash cooling. Multi-stage compression because we have multiple compressors, multiple throttles, and in between we have a flash chamber. Now you can do multiple flash chambers. You could have more than 2. You could have many compressors, many mixing chambers, many throttles, and many flash chambers. And you can endeavor to increase the coefficient of performance even more, okay? But this is one of the more standard approaches to increasing performance of a vapor compression refrigeration system. More of a standard approach. Okay, one last thing I want to say. I realize, just provided I hit the button to terminate, I do want to point out that the mass flow rates through the various parts of this device are different. So, for example, if we have a mass flow rate in the evaporator, there's our mass flow rate in the evaporator. It is not the same as the mass flow rate through the condenser. Why? Because some of the mass flow rate through the condenser is siphoned off, bled off, and piped into the mixing chamber. So if I have an M dot bleed here, M dot, I'll call this just M dot bleed, the saturated vapor bled off from the flash chamber, then M dot evaporator, M dot evap is equal to M dot of the condenser. So we have M dot of the condenser minus M dot bleed. So the amount of refrigerant flowing through the bottom half of the cycle is the amount flowing through the top half on the condenser minus what is bled off in the flash chamber. So when you do your calculations for power, W dot for the LPC, W dot for the HPC, Q dot for the evaporator, Q dot for the condenser, when you do your actual energy transfer rate or power calculations, the M dots will be the same. The M dot through the low pressure compressor is M dot evaporator. The M dot through the high pressure compressor is M dot condenser. The flow rate through the condenser is M dot condenser. The flow rate through the evaporator is M dot evaporator. These are not the same. And the difference is the amount bled off in the flash chamber. Okay? All right, just wanted to add that so there's no confusion. Take care, ladies and gentlemen.